So this is the first lecture of the second half of General Chemistry, Chem 222. What you're looking at here in this document are my lecture notes, which include the full year's sequence. So the lecture notes should have a table of contents depending on what PDF viewer you're using. And for Chem 222, we're going to start right here in the solutions and colloids chapter. Okay, so Chem 120 covers all of these, these first 10 chapters, and then chapters 11, 12, 13, 14, 15, 16, 17, and this would be chapter 21 from the OpenStax textbook. That's going to be the content of Chem 222. And so in this first, let's see, I'm going to hide this here real quick. This first chapter, this is the chapter opener for chapter 11. I'll switch to, I was trying to switch to full screen. There we go. This slide is my chapter opener. You'll see the figure here, which is actually from the textbook. It's a picture of a very nice looking coral reef, and the idea here is that the ocean water in the coral reef contains a lot of dissolved compounds, and so it's really a solution. The second part of the title, the colloids, is a different type of mixture. It's actually a heterogeneous mixture. We'll talk about those at the end. So the bulk of this chapter deals with solutions, and then at the end we'll talk a little bit about colloids. So this is the section opener. So this is the first section of the chapter entitled The Dissolution Process. And what I've got listed on the slides here are the learning objectives from the chapter. And as you read the chapter, I suggest that you take a look at the learning objectives for each section, maybe even write them down if you find it helpful, and then try to turn your reading into a bit of a scavenger hunt, in the sense that by the time you finish this section, you want to take some notes over these learning objectives and then go back and ask yourself if you understand the learning objectives. So for this particular chapter, we're going to be describing the basic properties of solution and how solutions form. This second learning objective, I feel that it's spread throughout the entire chapter. So while we might not have a specific, there will be some aspects of this. So you'll find some aspects of this learning objective in this chapter or in this section, and then it's also going to be carried on in other sections as well. So this is almost a learning objective for the entire chapter, so to speak. And then let's see. Yes, we'll also talk a little bit about the thermodynamics of solutions. So just some basic definitions. In this chapter, we're exclusively focusing on aqueous solutions, and so we'll have in mind aqueous solutions as we continue through this chapter. We'll also talk about maybe not exclusively aqueous solutions. We'll also talk about solutions of two volatile liquids as well. This slide is just meant to provide the basic definitions of a solution. So a solution is a homogeneous mixture of two or more substances. The term homogeneous means that the components of the solution are mixed at the atomic or molecular level. That is, when you look at the solution, say under a microscope, you can't tell the difference between one part of the solution and another part. And that is because the components, the solute and the solvent, are mixed together so uniformly that it does so at the molecular level. The term solvent refers to the component of the solution that is present in the greatest concentration. The solute, or solutes, if there's more than one solute, are the components that have a much smaller concentration. Okay, so whatever the solution consists of mostly, that's the solvent. And then the parts of the solution that are present in smaller amounts are called the solutes. I mentioned this earlier. When water is the solvent, we call it an aqueous solution. And I've got two examples here. Here we're making a glucose solution, some type of sugar solution. So here we've got our sugar. It's a solid. We dissolve it in water, and that gives us the dissolved solute. This would be an example of a molecular compound that forms that's combined with water to form a solution. Down here we have an ionic compound, potassium dichromate. It's mixed with water. The potassium dichromate is this red-orange crystal. You mix it with some water, and then you get a red-orange solution. And if you look closely at the solution, you won't be able to see individual crystals of the potassium dichromate. It's completely mixed, at the atomic and molecular level with the water. Okay? And so that's why it appears transparent. You can see right through it. It looks totally evenly distributed. You can't tell the difference between the solute and the solvent. It all looks the same at the macroscopic level. So notice that this was an ionic compound, right? We have a metal cation and a polyatomic anion, and when that dissolves in water, the ions dissociate from one another, and we have an electrolyte solution. So an electrolyte solution is one where you've got ions dissolved in the solution. So just a list of properties. We've already talked about homogeneous. Another property of solutions is that that they are stable, in the sense that the dissolved solute will not separate from the solvent. You can let the solution sit there, and it's going to sit there forever, and you're not going to get that solute to come out of solution. Now, there are mixtures that are not stable. So, for example, the colloids that we'll talk about. Well, not the colloids. I would say for example, a suspension that can, like mud water. Okay, so if you take some lake water, or some mud, and let it sit in a jar for a really long period of time, eventually all of the sediment is going to settle down to the bottom, and then you'll have mostly solvent, the water, at the top of the solution. A true solution won't do that. So, for example, this potassium dichromate solution, it's going to stay dissolved forever. Okay, it's stable in this sense. Another aspect of solutions is that you can vary the concentrations of the solutes within certain limits. So you can't put an indefinite amount of solute in a given amount of solvent, but you can to some degree control the concentration of the solute that's dissolved in the solvent. Here I've provided two qualitative descriptors for solutions. A dilute solution is one where the solute concentration is relatively small, versus a concentrated solution is one where the solution concentration is very large. There's different types of solutions. So you can have gaseous solutions, like air is a mixture of different gases, and they're mixed at the atomic level, and it's stable. You can also have liquid solutions, like we've been talking about, and there's also solid solutions. So, for example, metal alloys, like brass down here, which is a combination of zinc and copper that are mixed together at the atomic level. So different solutions can have different phases. Like I said, we're going to be talking mostly about liquid solutions and aqueous solutions in particular, but you can have any of these types, and that is usually, not always, usually determined by the phase of the solvent. There are exceptions to that. Here's some examples of solutions. Down here, air, as I mentioned, mostly nitrogen, but there's also oxygen, of course, carbon dioxide, and trace amounts of other gases. Soft drinks, so you're going to have sugar, water as the solvent, and you'll also have dissolved carbon dioxide as well. Here's an example of a gas that's dissolved in a metal, so a palladium surface that has hydrogen gas dissolved in it. Rubbing alcohol, I forget which alcohol it is. I believe it's isopropyl alcohol. I can't remember for sure. Alcohol and water. I believe it's usually 70% alcohol, and the rest is water. Salt water, of course. All sorts of different minerals are dissolved in the salt water. And then I already mentioned the brass. Let's see, what do we have next here? Okay, so we're going to talk about how solutions form next. So when solutions form, they form spontaneously. That is, they form on their own. So if you take the solute and put it inside the solvent, it will automatically form the solution, so long as the solution does form. We'll look at later on a picture where, and you know the example, oil and water don't mix. So oil and water don't spontaneously form a solution. But when the solution forms, it forms on its own. The term spontaneous is actually a somewhat technical term in thermodynamics. A spontaneous process is one that might occur on its own without the need for any external energy. And in this class, we are going to discuss thermodynamics in more detail later on. And we'll talk about, the impact of energy, which has to do mainly in chemistry with the interactions between particles, and entropy, which is something that we haven't learned about yet. And you can think about that in different ways. One common way of thinking about it is in terms of molecular disorder. And as I said, we'll discuss this in more detail. For right now, I'll just have you take my word for it that when you randomly mix two substances together, that increases the entropy of the system, and that tends to favor the formation of that solution. Okay, so mixing increases entropy, and that favors the formation of solution. As I said, don't get hung up on the entropy thing. We're going to spend a lot of time talking about it later on in the course. For now, just take it as a given that if you mix two things together, that tends to favor that process for occurring. Mixing, on the other hand, can be both. It can be either endothermic or exothermic. That is, the energy of the system can go up or it can go down, and that just depends upon the nature of what it is that you're combining, how they interact with one another. The diagram at the bottom is meant to illustrate the entropy effect of mixing. So you see here we've got two vessels one contains helium, the other contains argon. If you open the valve between these two vessels, the expectation is that they will spontaneously mix through diffusion until the concentration of helium on both sides is the same, and the concentration of the argon on both sides is the same. And no matter how long you wait, they will never spontaneously unmix. Right? So there's there's a natural direction of spontaneous change here. The unmixed state versus the mixed state, the system will spontaneously go to the mixed state and will never on its own go back to the other state. Okay, that in a nutshell, that's due to entropy, and we'll talk about that later on in the course. We're going to focus on the energy effect right now because that's something that we do have some experience with from Chem 120. And so there are three types of interactions that are important, three generic types of interactions that are important when you're thinking about solutions. These are the interactions between the pure solute particles, the interactions between the pure solvent particles, and then the interactions between the solute and the solvent. And these interactions that I'm referring to, these are things that we've studied in the past, the intermolecular forces between molecules. So if you've got ions in the solute, the ion-ion Coulomb interactions are very important. If you're dealing with an ionic compound being dissolved in a polar solvent, one that has a dipole, then the ion-dipole interaction will be very important. If you've got a nonpolar solvent, then the ion can induce a dipole between in the nonpolar solvent, and so that will lead to an interaction. You've also got, if you have, say, a polar solute and a polar solvent, the dipole-dipole interaction will be important. Or if you had a polar and nonpolar solvent, the dipole moment of one species will induce a dipole moment on the other, and that's going to lead to an intermolecular attractive interaction. All molecules, all ions, they all experience a London dispersion interaction. Anything with electrons is susceptible to this interaction, so this one's quite important. And then for certain types of molecules that have an electronegative atom bonded directly to a hydrogen atom, we've learned previously about the phenomenon of hydrogen bonding, which can be quite strong and give rise to unique properties. So all of these things that we've studied in the previous semester, Gen Chem 1, these are the types of interactions that I'm talking about here that we need to be aware of. The next couple of points here are, well, they're talking about, in order to form the solution, you need to break the interactions between the solute particles, right? You have to separate the solute particles from one another in order for them to be dissolved. And what I'm calling that right here, I'm calling that the lattice energy. And so we can think of this, commonly you would associate the lattice energy with an ionic compound. So something like sodium chloride or lithium fluoride or something like that, where the ions are held together through these ion-ion Coulomb interactions. And in order to separate the ions, you need to overcome this lattice energy. You also have to separate the solvent particles from one another in order to make space for the solute. Okay, so you have to, in order to form the solution, you have to make space between the solute particles and space between the solvent particles. This means that you're breaking intermolecular bonds. Okay, so the bonds that keep the solute together, that keep the solvent together, you have to overcome those bonds. And whenever you break a bond, whether it's an intermolecular bond or a covalent bond or an ionic bond, it always costs you energy. So that's an endothermic process. So when you break these solute-solute and solvent-solvent interactions, that's going to raise the energy of the system. However, when you solvate the solute, that is, when you bring the solvent in contact with the solute, you're going to be forming new solute-solvent interactions. And that is going to lower the energy of the system. So that part of the process is exothermic. So when you break intermolecular bonds, it's endothermic. When you form new intermolecular bonds, it's exothermic. Now, whether or not the overall process of forming the solution is endothermic or exothermic is going to depend upon the nature and strength of these different interactions. So the so-called enthalpy change for a solution, the net enthalpy change for the dissolution reaction, could either be endothermic or it could be exothermic. And we've learned previously what delta H means. For an endothermic process, delta H is positive. For an exothermic process, delta H is negative. Here's a diagram illustrating what I've been talking about. Okay, so you can think of the formation of a solution as a three-step process, at least conceptually. You need to break intermolecular bonds in the solute. you need to break intermolecular interactions in the solvent. And then when you bring the two together, you're going to be forming new intermolecular interactions between the solute and the solvent. Now, in reality, all of these three processes, they all happen at the same time. But from a conceptual perspective, you can think of them as being distinct. The net process can be endothermic or exothermic. And we'll talk a little bit more about that as we go throughout this chapter. On this slide, I'm going to introduce what's called an ideal solution. And so that's a model that we're going to be using to think about solutions. The ideal solution is one where the solute and solvent interactions are the same. That is, they have the same magnitude and the same strength as the interactions within the pure solute and the interactions within the pure solvent. Okay, so of those three interactions, we're assuming that all of them are about the same. We want to be careful, though, when we see the word ideal, we don't want to get confused with ideal gases. Okay, there's a big difference between an ideal solution and an ideal gas. Gaseous solutions are almost always ideal, and that's because, by definition, ideal gas molecules do not interact with one another at all. So therefore, if you've got a mixture of helium and xenon gases, right? The interactions between the molecules are assumed to be so small that we can neglect them. So of course the interaction between helium and xenon atoms is going to be the same as the interactions between helium atoms and helium atoms and xenon atoms and xenon atoms. The interactions are all zero. Okay, so an ideal gas solution is always ideal. However, for condensed phase, quote, ideal solutions, the interactions are not zero. In fact, the interactions must be strong and attractive. Otherwise, you wouldn't have a liquid phase. You wouldn't have the condensed phase. It would have to be gaseous if there were no interactions. So in the ideal solution, we are not neglecting interactions. What we are doing is we're saying that all of the interactions are about the same. Okay, and that'll be true for certain circumstances. Okay, so those circumstances are that the solute and solvent molecules should have similar size. They should have roughly the same shape and chemical structures that aren't too different from one another. Otherwise, if the solute and the solvent are really different from each other, the interactions between the solute and the solvent could not be the same as they are between the solute and solute and the solvent and solvent. So the ideal solution, it's fairly fictitious in the sense that most solutions are not ideal. That is, most solutions do not fit this criteria, but some do. And then what I've done is I've listed a few very good examples down here, and I wanted to write out the structure of these molecules to illustrate that. So methanol and ethanol, these are both alcohols. So methanol has the formula CH3OH, and its chemical structure, the structural formula, looks like this. So this is not a hydroxide compound, it is an alcohol. What makes it an alcohol is it has a carbon, OH. Okay. So one common mistake is students will see the OH in the formula and they'll think to themselves, oh, that's a hydroxide. Well, a hydroxide compound is one where you have the hydroxide anion present. And so something like, just as an aside here, something like sodium hydroxide, right? This is not an alcohol, that's a hydroxide. You have a metal cation, so I need to recognize sodium as a metal. Correspondingly, the hydroxide here is going to be an anion. So here, these guys are present as, this is an ionic compound because you have a metal bonded with a polyatomic anion or a nonmetal. Very different from methanol here. Everybody in this formula is a nonmetal. Okay, and so when you see all nonmetals and you see the OH group, it's not a hydroxide, it's an alcohol. There's a covalent bond between the carbon and the oxygen. Here, it's an ionic bond between the sodium cation and the hydroxide anion. Okay, so it's important that you can distinguish hydroxides from alcohols. So that's methanol. Ethanol has the formula C2, let's see, I think it's H5OH. I'll double check that in a minute. Let's draw the structural formula for ethanol. We've got the CH3, then there's another carbon, 2 hydrogens, like so. And so again, you see that carbon OH, that is an alcohol. Both molecules are alcohols, and they have similar shapes and similar chemical structure. Ethanol is not that much bigger than methanol. And so these two compounds, they're both liquids. They form an ideal solution. Methanol is the active ingredient in windshield wiper fluid. Ethanol, as you know, is the active ingredient in alcoholic beverages. It also has a lot of uses in chemistry as well as a solvent. So these two guys form an ideal solution. Let's look at benzene and toluene. Let's see, so benzene is C6H6. It's a solvent. Let me draw the structure here. It's an interesting structure. You may have seen it before when you did Lewis structures. It's a little ring of 6 carbon atoms. Each one is bonded to a hydrogen atom, like so. And then to get octets, you need to make some double bonds. And there's a resonance structure, and I won't draw that, where you put the bonds on the other 3 carbon-carbon bonds. And so this is benzene. Toluene here, which I'm going to get the count wrong. Let's see, C7, so subtract 1 and then add 3. So H8, I'll count them afterwards. Toluene it's got that 6-membered ring, but then there's a CH3 group up here. And again, you've got the double bonds here, and there would be a resonance structure. Let's see, did I get the formula right? So we got 1, 2, 3, 4, 5, 6, 7, 8, 6, 7. Looks like I did. So these two molecules, they have similar shape, similar chemical structure, similar size, right? The methyl group, the CH3 group, it's called the methyl group. It's not that big. It is bigger than a hydrogen atom, but these are roughly the same size. And the benzene and the toluene, they form an ideal solution. We'll do one more example. We'll look at some hydrocarbons here, pentane. And I'm going to draw the structure first and then write the formula because it's easier for me. So pentane, the penta means you have 5 carbons. There's 4, 5. And then each carbon has 4 bonds. And they're bonded to hydrogens. So we've got 3, 6, 7, 8, 9, 10, 11, 12. Okay, so that's pentane. That's its structure. Right there. And then we can do hexane. 1, 2, 3, 4, 5, 6. It's the same deal. The rest of the bonds are all to hydrogen. So these are both hydrocarbons. They have the same chemistry. They're close to the same size. 14, 6, 7, 8, 9, 10, 11, 12, 13, 14. Same size, same chemistry. Pentane and hexane form an ideal solution. What about interactions? I didn't mention interactions. I should have. Here, you wouldn't expect a dipole moment for these molecules, at least not a significant one. And so the pentane and the hexane, we would classify these as nonpolar molecules. And so the interactions within the pentane and the interactions within the hexane are going to be the same as the interactions between the two. What's going to be the dominant interaction? Go back to our list here. Of these interactions, which one do you think is going to be the most important for nonpolar molecules? It's the London dispersion interactions that are the most important. Going back to benzene and toluene. Benzene is perfectly symmetric. Okay, so it's not going to have a dipole moment. Toluene is going to have a slight dipole moment due to the methyl group here, but it's not going to be big. And so generally speaking, these are nonpolar molecules. And so again, what interactions are going to be at work here? It's those same London dispersion interactions that are important. How about the two alcohols? Well, they're polar. They have this OH group on them. Okay, so there's going to be some dipole-dipole interactions. But among this list of possible interactions, which would be the strongest and most dominant? Well, if you see the electronegative oxygen bonded to a hydrogen, that indicates that hydrogen bonding is going to take place. And so hydrogen bonding is going to be the dominant interaction in this solution. Just for comparison, what about a sodium hydroxide water solution? Okay, so water is the solvent. We'll let the solid sodium hydroxide be the solute. You mix them together, it forms a stable solution. What interactions are going to be at work there? Well, you're going to have ions dissolved in a polar solvent. It's going to be that ion-dipole interaction is going to be important. What are the interactions that are at work in the pure solute and in the pure solvent? Well, you're going to have ion-ion interactions in the pure solute. Those are very, very strong. You're also going to have dipole interactions within the solvent, right? Water's a polar molecule. And then those are very different from the ion-dipole interactions between the solute and the solvent. And so the electrolyte solution, right, the sodium hydroxide solution, is not going to be an ideal solution because it doesn't satisfy this notion that the ions in the solvent have the same size, shape, and chemical structure. They're totally different. Okay? And so electrolyte solutions are almost never, ever, no, they are never ideal. Okay? But when the solute and solvent have the same properties, then the solution behaves ideally. Well, we'll talk more about electrolytes in the next video.